How can one charged object influence another without touching it? Why does a rubbed balloon stick to a wall? How does a capacitor store energy? And how do antennas ultimately generate electromagnetic waves? The answer begins with one of the most fundamental concepts in physics and RF engineering, the electric field. Suppose you place two electrically charged objects near each other. Even though they never touch, they can attract or repel one another. This phenomenon has been observed for centuries, yet it raises a fundamental question. How does one object exert a force across empty space? Early scientists struggled to explain this action at a distance behavior. If nothing physically connects the objects, what mechanism carries the force from one location to another? Simply saying that charges attract or repel does not explain how the interaction occurs. To solve this problem, physicists introduced the concept of the electric field. Instead of charges acting directly across space, each charge creates a field around itself. Other charges entering that field experience a force. This idea became one of the cornerstones of modern electromagnetism. An electric field is a region of space in which an electric charge experiences an electrical force. It describes how a charge influences its surroundings and provides a way to predict the force that another charge would experience at any location. The electric field is represented by the symbol E and has both magnitude and direction. By convention, the field direction is defined as the direction a positive test charge would move if placed within the field. This allows engineers and physicists to visualize how charges interact. Electric fields can be generated by static charges or by changing electromagnetic systems. In RF engineering, time-varying electric fields are especially important because they participate in the formation of electromagnetic waves that carry information through space. Intuitively, imagine placing a heavy ball on a stretched rubber sheet. The ball deforms the sheet, changing the surrounding environment. A smaller ball placed nearby will respond to that deformation. Similarly, a charge modifies the space around it by creating an electric field. Physically, consider a positive electric charge. The electric field radiates outward in all directions. If another positive charge enters the field, it experiences a repulsive force. If a negative charge enters the same field, it experiences an attractive force toward the original charge. Mathematically, the strength of the electric field decreases as distance from the source charge increases. Charges that are close together experience stronger forces, while charges that are farther apart experience weaker forces. This behavior explains why electric interactions can act over large distances yet become less significant with increasing separation. Electric fields play a central role in RF engineering because they are one of the two components of electromagnetic waves. Whenever an RF signal is transmitted, oscillating voltages create changing electric fields around the antenna structure. Inside transmission lines and RF circuits, electric fields store and transfer energy. Capacitors operate by storing energy within electric fields between conductive plates. Understanding field distribution is therefore critical for circuit design and electromagnetic analysis. At the system level, electric fields influence antenna radiation, signal propagation, microwave devices, waveguides, and wireless communication links. Nearly every RF component interacts with electric fields in some way during operation. The electric field is one of the fundamental building blocks of electromagnetism. It provides the mechanism through which charges interact and serves as a key participant in the generation and propagation of electromagnetic waves. A common misconception is that electric fields exist only when current is flowing. In reality, even stationary charges create electric fields. However, changing electric fields become especially important because they can generate magnetic fields, leading to electromagnetic wave propagation. Understanding electric fields is only half of the picture. Electromagnetic phenomena arise from the interaction between electric and magnetic fields. To understand how electromagnetic waves form and travel through space, we must next explore the magnetic field. In this lesson, we learned that electric fields describe how electric charges influence the space around them and create forces on other charges. We also saw how electric fields play a fundamental role in capacitors, RF circuits, antennas, and electromagnetic wave generation. In the next lesson, we will explore the magnetic field and discover how moving charges create magnetic effects that work together with electric fields to form electromagnetic waves. If you found this useful, like the video, subscribe, and follow for the next lesson.